So we're continuing with our chapter 7 that deals with sampling distributions. This time we are applying sampling distributions with sample proportions. So we'll be able to remember that a sampling distribution is the distribution of all possible samples. So in this case, we'll be thinking about the distribution of all possible sample proportions from all possible samples. Here we'll look for the mean and the standard deviations of the sampling distributions. We'll have to check a number of conditions when we get to our 4-step process. So we're going to check the 10% condition. That's dealing with the independence violation. And we're going to make sure that we're not violating it too much by only sampling less than 10% of the population. And then after we've checked that, we can calculate our standard deviation of the sample proportions. If the sampling distribution of the sample proportions is approximately normal, all right, we're going to check that condition. We're going to determine whether or not we can assume approximate normally distributed sampling distributions of our p hat. And then we will, once we've decided that it's normal, then we will use the normal distribution with the given mean and standard deviations to calculate probabilities that we would get such sample proportions. Okay, so we're going to look at here a simulation. So we're going to have, we're going to look at a applet that comes along with the book. And it's a candy machine, and we want to look at the proportion of candies that is orange. And this little web-based applet is going to let us make some adjustments. Now, your paper copy has the picture of this candy dispensing machine in the top right corner. However, if you go to the electronic version of the PDF, so if you go to this the electronic version of this page and click on this candy machine, it will actually take you. It's linked to the web-based software that will allow you to do these simulations that I'm going to discuss. So if you want to sort of pause this and go look at that PDF and click on it and open that up, I would say print. If you have all your PDFs printed out, then it'll be easier to kind of follow along. All right, these are going to be what you are inputting. You can notice that I have 6 different graphs here. Along the top row, with all 6 of these, we're dealing with 500, in each case, 500 samples. So these are not sampling distributions, rather they're approximate sampling distributions. We have 500 samples. And so along the top, we're going to pretend that the proportion of orange candies in the machine is 15%. And what happens as we go across the top row is that our sample size of 50 on the first one becomes sample size of 25, and then sample size of 10 as you go across. If you look at those more closely, you can see that. And on the bottom row, we're going to vary the sample sizes again, but we're going to assume that the proportion of candy in the population is 45%. Okay. So when you click on the electronic version of that page, and it takes you to this, then there's a couple things you want to adjust. So you first want to turn on the proportions for orange. We don't want to talk about the number of orange. So we're dealing with proportions here, not like a random variable as the number of orange candies. We want the proportion of orange candies. And then you're going to make sure that you adjust the number of samples. That's 500. We're going to keep those the same every time. And then the number of candies, that's the sample size, right? The number of candies I'm going to draw every time is 50 to start with. And then the proportion of orange candies that's in the population of the machine, that'll be 15. So the 15% will get changed in the bottom row to 45%. And then the number of candies, or the sample size, will change from 50 to 25 to 10 as you go across those rows. Then what you'll do is you'll click on this button that draws the samples. You can turn on the animation if you want. It slows it down a little bit, but and so then it will give you a distribution like this. So this is a dot plot. There's just 500 of them, so the dots are crammed together so closely it looks like little vertical lines, but these are stacks of little dots. Notice too that this is the situation of the top left corner, where the proportion of candies in the population is 15%, and the sample size n is the number of candies is 50. Now the distribution I'm showing here is going to be different than the distribution you have on the paper, or if you do this yourself and run it every single time, it's going to be slightly different, because again, this is not the actual sampling distribution. This is an approximate sampling distribution with 500 samples, and you will get different outcomes every time. All right, you can also select this down at the bottom that says normal approximation, and that will superimpose a normal curve on top of our approximate sampling distribution. So you can see here that it's superimposed on there, so you can kind of compare it to the normal and see how close it is to normal. And that's kind of the whole point of this. As you work with the 6 different settings for the 6 different distributions, approximate sampling distributions, you'll see when is it more or less normally distributed. And again, every time you run it, it's going to look a little different. Sometimes they might look pretty awful, but we'll hopefully kind of see a pattern. All right, so what we want to look at is, you notice as you moved around the 6 different approximate sampling distributions on this page, you notice that what we were changing was the P, the proportion of candies, either 15 or 45%, and the sample sizes from 50 to 25 to 10. So we want to look at particularly what causes some of these sampling distributions to look a little bit more normal than others. So and the only thing we modified when we were looking at these is the N and the P. So if we look at what N times P is, again, these are the values up here that you're adjusting as you put these things into the web-based Candy simulator. But let's now look at your N and your P. And so if we take N times P for the first one on the top left corner, we get 7.5. And then we do N times 1 minus P. That's the proportion of non-orange candies times N, and that's 45. And you notice that the distribution looks fairly normal, not perfect down in the left tail, doesn't really fit in there perfectly, but it looks fairly normal. If we look at the next one going across the top, you can see that the values of N times P are kind of getting smaller. That's because our sample size got cut in half, so it makes sense that those values are cut in half. And then we're making N even smaller. And so let's look at this middle one again and think about how here it is a little less normal looking. And then in the last case, on the top, now it's not looking normal at all. It's definitely skewed to the right. The left tail has no values in that distribution that match the normal curve. So it's really bad there. All right, so now let's look down at the bottom where the proportion of orange candies in the population was 45%. First one looks pretty well normal. And we can look at the n times p and n times 1 minus p, and those are both pretty large. They're in the 20s. The next one, still pretty large, and the sample and the sampling distribution looks still pretty normal. And even in the last one, it still looks fairly normal. Okay, so we know we're going to have, to determine whether or not our sampling distribution of the p hat here is normal or not. Definitely seems like it's going to be affected by the n and the p value. And so we'll investigate that. Also notice that in the bottom where the p hat, the proportion of orange candies is 45, it's pretty close to 55 or 1/2. Then in that case, in the approximate sampling distributions seem to be pretty normal. And that will be the case when we find that our p-value is close to 1/2. Up at the top, all of these at the top row had a proportion of orange candies much smaller, 15%. And certainly in this last case, this is certainly not normal, and we would not be able to assume normality. Okay, so what did all that show us about the shape, the center, and the spread? So in some cases, we found that the sampling distribution of p hat was normal. It seems to be dependent on our n and both our n and our p values, the sample size and the population proportion. All right, the center of each of those, if you look back at your other, the first top 3 all seem to be centered right at 15%. The bottom 3 seem to be centered at 45%. And that's because the mean of the sampling distribution of p hat will be equal to the true proportion in the population, and that is because p hat is an unbiased estimator. So we learned that back in section 7.1. Yes, the mean of the sampling distribution of p hat will be always equal to the population proportion p. And then the spread, kind of hard to reference it now, but look back at your last the page with the 6 graphs on it. As the sample size n got larger, we can see that the spread of our sampling distributions got smaller. So look at those again and confirm that that is the case, but you'll see that that definitely is the case. All right, and then we could think of the number of orange candies as a random variable x, but if we divide that by the sample size we took in each case, then that would give us our sample proportion, or p hat. So it's the count of the orange candies that came out, x, the random variable, divided by the sample size. All right, and so if you remember back in chapter 6, we talked about the mean and the standard deviation of the binomial random variable x. And so really that's very much related to what we're doing here, because in order to get our random variable for all the possible p hats that could come out, we would simply take the random variable x, the number of successes, and we would divide that by n. Or if we want to think of it in another way, instead of dividing by n, we could think about multiplying by 1 over n. And that might help us to evaluate the following formulas. So if we look at the original the mean of the random variable x, np, and so all we're doing to get the mean of the sort of new random variable p hat, the mean of the sampling distribution of p hat will really just be 1 over n times that other mean, which was np, and then we can simply cancel out our n's, and that would leave us with P, which is again in one more way of verifying that P hat is an unbiased estimator, because the mean of its sampling distribution will always be equal to P, the true proportion in the population. And we can use some a little math to do the same thing with the standard deviation. So the standard deviation for the random variable x was, if our binomial random variable x was given to us in the previous chapter, if we take that formula and multiply it by 1 over n, which is sort of the transformation we're doing, then we normally don't do this, but we could take that 1 over n and move it into the square root, and so that would give us an n squared in the denominator. And then one of these n's will cancel with one of these n's and leave us with just n downstairs. And so that's how we can get the other, the standard deviation for the sampling distribution of p hat. And so that's another way of sort of also verifying that indeed the all else being the same, as the sample size increases, the spread or the standard deviation is going to decrease because that larger number is in the denominator. All right, so this just kind of reiterates what we just saw. The mean of the sampling distribution of p hat is simply going to be equal to p. And that's also because we learned in the last chapter that the last section that p hat is an unbiased estimator of p. So the mean of the sampling distribution of p hat will be at the value of the parameter p. And then a standard deviation, that's given by this formula here. It reiterates the fact that that as n gets bigger, the standard deviation gets smaller. Okay, also one more thing we need to talk about here is that in order to calculate that standard deviation, we have to first check our our 10% condition, that we're not sampling more than 10%. This it allows us to assume that our violation of the independence rule is not so bad, and so it's not going to cause us to be off in our calculations by that much. All right, and then last thing we want to check. We're going to start, having to check a lot of stuff when we start looking at our 3 and 4 step processes. And so here we need to know, in order to do calculations as though the sampling distribution of p hat is normal, we have to first know that the sampling distribution of p hat is normal, and we check that by looking at the large large count condition, and that is that we look at n times p, is that greater than or equal to 10, and also n times 1 minus p. So it's the expected successes and sort of the expected number of failures. They must both be greater than 10. And then, so we refer to that as the large count condition. Okay, so n times p, and then where p is the proportion in the population, and then n times 1 minus p, which is the proportion of like failures in in our case, the example we were doing was in the proportion of not orange candies. Okay. All right, so what are we doing here? We have a whole population, and we have certain proportion, right? So we have a population, we have a proportion, we might graph it. If it's the orange candies, we might have something like, okay, this one, 55% of the candies were orange, 45% of the candies are not orange. And we might sample. So again, we're talking about the sampling distribution. What is that going to look like if we took lots and lots of samples? Not all of those samples would be exactly the same as the population distribution. But we take all of those, if we took every possible sample and we plotted it in in each one of those p hats got plotted, then we would have the sampling distribution. Now, more often than not, we don't have a sampling distribution. It's a theoretical thing. So if we're doing a simulation, then it's going to be an approximate sampling distribution. All right, let's look at an example. And we'll use our quite extensive three-step process for this example. All right, a superintendent of a large school district wants to know what the proportion of middle school students in her district are planning to attend a four-year college or university. Suppose that 80% of all middle school students in her district are actually planning to attend four-year university or college or university. Now, in reality, we won't know this 80%, but this is more of a hypothetical, theoretical type question. All right, so if 80% of the middle school students are actually planning on going to college, then we want to know what is the probability that an SRS, a simple random sample of size 125 middle school students would give a result that's within 7% of the true value. So 7% within 7% of the true proportion of 80%. So the first thing we want to do is come up with, first of all, step one. So step one is going to have quite a few things in it now, because there's a couple of things we have to check before we do calculations in this situation. So first, let's write down what probability is that we're trying to calculate. So we're trying to calculate the probability that our sample would give us a p hat that's within 7 percentage points from 80. So that would be that our p hat is between 73% and 87%. Okay, so we have lots of things that we want to check here. So first, we know what the mean is of our distribution. Our sampling distribution has a mean of 80. We're assuming that we know the population proportion is 80. And so since p hat is an unbiased estimator, we know that the sampling distribution of p hat will have its mean at the true p value of 80%. Okay, so now we want to think about, well, what is the standard deviation of our distribution? Now, before we can calculate the standard deviation, we have to check our 10% rule. So we sampled 125 students. We have to know that in this district, it is a large district, so probably safe to assume, but we have to assume that there are at least 1,250 middle school students in this district. Otherwise, we've sampled more than 10%. So there's at least 1,250 middle school students. All right, once we make that assumption, then now we are allowed to calculate our standard deviation. All right, so the standard deviation, using the formula we were just talking about a couple slides ago, p, it's a square root of p times 1 minus p divided by n. And so that ends up being 0.036. All right, so now we want to know whether or not we have our mean, we have our standard deviation. Those two things are always true regardless of what the shape of our distribution is. But we'd like to know, is the shape of our sampling distribution, is it normal? So we need to check n times p, and we need to check n times 1 minus p. We need to show that both calculations, 100 and 25, are both over 10. And so because of that, we know that our distribution of the sampling distribution of p hat is approximately normal. And then we also would just want to say, well, what it is. So it's normal distribution with a mean of 0.8. Again, because it's a sampling, it's a unbiased estimator. We know that that's the same, and the standard deviation. All right, so on step 2, we want to actually perform our work. So we could still go back and use our z-scores if we wanted, and then go to our z-score table and come up with our probabilities. We also want to make sure that we're including a normal curve with labeling and shading. All right, so we could, from our z-score table, find the two probabilities and subtract them, and we would get something close to 95%. We can certainly do that as well with our calculators, and that's what I would expect that most of people are doing at this point. You're not really going back to your z-score table calculations. You're going to use your normal CDF. All right, so remember when you write these down on your paper, you have to include lower, upper, mu, and sigma as bare minimum, just to show that you know what those values represent. Again, you're not putting those terms into your calculator, just the numbers. All right, and you can see that the two numbers are close. They're both about 95%. And the last thing we want to do is simply answer the question. All right, so about 95% of all the SRSs of size 125 will give a sample proportion within 7 percentage points of the true proportion of middle school students who are planning to attend a 4-year college or university. So 95%, about 95% of the samples that we take would fall within plus or minus 7 percentage points of that 80. That 80%, which is the proportion of middle school students in the entire population who are planning on going to college. Okay, so this is your homework. Number 35D is a 3-step problem. Make sure that you're following the model that we showed on the last slide. Step 1 is the most intensive. For step 2, make sure that, I would encourage you to just use your calculator's CDF, but regardless of what method you use to actually calculate the probability in step 2, make sure that you're including a normal curve with shading and labeling.